Hi, my name is Belén Martinez and I work as a researcher in Tecnalia. Welcome to this webinar. This is the first of a series of webinars based on the BETaaS project. The purpose of this session is to present the BETaaS platform to the audience, focusing on the semantic capabilities of this platform. The BETaaS platform is a platform for the IoT that has been developed under the scope of the BETaaS project, which is an FP7 project formed by an international consortium. The Internet of Things resides on the concept that the connection of things in the physical world to the Internet provides both access to remote sensor data as remote control over the physical world. This has opened the door to the development of a number of monitoring and control solutions able to solve problems in specific areas. But due to the complexity of IoT systems, usually composed of multiple and different equipment, and the lack of standards on compatibility between that equipment, such solutions typically provide isolated vertical support targeted at specific fields. To overcome these limitations, we need a horizontal approach based on a common reference model to expose standard interfaces to communicate with small things, and this is exactly what BETaaS offers. The BETaaS platform is a horizontal runtime platform that provides an environment for applications accessing machine-to-machine services and devices through a set of services. Currently, there are several initiatives whose goal is to define a horizontal platform for IoT. Though these initiatives offer horizontal platforms, they don't fulfill important requirements for IoT, like quality of service, dependability, or context awareness. Besides, these platforms are based on centralized cloud architectures, which may find difficult to cope with end-to-end characteristics such as high mobility, high number of nodes, or low latency. BETaaS provides a new vision about the way to expose and manage things in the Internet of Things through a distributed runtime architecture that seamlessly integrates existing heterogeneous M2M systems composed of different things by means of adapters within a gateway. Besides, BETaaS provides platform-level support of context awareness, security, quality of service, and dependability. This presentation will be focused on the semantic capabilities of the platform. By means of semantics, BETaaS is able to integrate sensor networks of already existing cloud solutions from different vendors. The BETaaS platform is based on a distributed architecture that integrates different machine-to-machine systems by means of a set of BETaaS gateways, each providing access to its connected things. Each gateway shares the functionalities offered by the things of its end-to-end systems with the rest of the network. BETaaS provides an environment for applications accessing things as services. So once a thing is connected to a BETaaS gateway, the BETaaS gateway generates services associated to this thing so that an application would be able to access the thing by means of its associated services. The BETaaS platform has a layered architecture. Such a structure guarantees the proper level of abstraction and flexibility, both for applications at the top and for the integration of different systems at the bottom. At the bottom layer, BETaaS integrates heterogeneous M2M systems at the physical layer, thanks to the adaptation layer. The adaptation layer allows plugins to be dynamically deployed into the platform in order to allow the compatibility with different M2M systems. We have already developed two adapters, one for Etsy M2M sensors and actuators, and one for COPE sensors and actuators. Only the COPE adapter will be released as open source. The Things as a Service layer, or TaaS layer, provides a paradigm that allows the creation of a thing service for each thing connected to the platform. Thing services are created in a content-centric manner. This paradigm will be analyzed later. Finally, the service layer defines the platform interface to the external applications, exposing all available thing services in the platform as basic services. Following, you can see an example that tries to illustrate BETaaS' main purpose. Silvia has a home security alarm system composed of different presence sensors manufactured by vendor A. Silvia also has a home weather station composed of a temperature sensor and a humidity sensor manufactured by vendor B. By means of BETaaS, Silvia would be able to integrate the sensors provided by these two isolated vertical products. For example, Silvia has a smart watering valve and wants to water her garden when it's hot and nobody's at home. Silvia decides to use BETaaS to combine the information provided by the presence sensors of the alarm system with the temperature sensor provided by the weather station in order to activate the irrigation valve. Silvia downloads an irrigation application from the BETaaS repository and installs it in her BETaaS gateway. The application successfully combines the information from the different sensors. So how is BETaaS able to do this? By means of semantics. Semantic technologies are used in BETaaS to unify information that comes from heterogeneous sources, to infer new knowledge from raw data in a context-aware fashion, and to generate unique services names for each of the things connected to the platform. To get this goal, we have created the BETaaS ontology, which is a network of ontologies based on several relevant ontologies from the IoT domain. We use the domain model of the IoT project as a common vocabulary to link all the ontologies in the network. All the information retrieved from sensors and actuators connected to any of the BETaaS gateways is translated to a semantic format and inserted in the BETaaS ontology. BETaaS also takes into account the context of the things. This context is composed of elements such as the battery level, the communication protocol used, the available computing capacity, or information about the location of the thing. The location of a thing is defined in BETaaS by a collection of data like the geographical coordinates for outdoor scenarios only, the name of the city in which the thing is located, a keyword describing the location of the thing in a general way, and a descriptive text. When connecting a thing to a BETaaS gateway, some information about that thing has to be provided by the installer of that thing. For each of the things connected, BETaaS stores if the thing is a sensor or an actuator, its maximum response time, the measurement taken, information about the location, the type of the thing, the units of their measurement, the identifier of the thing, and the identifier of the device, as a device can be composed by more than one thing. This information is stored in the BETaaS ontology. The information is automatically captured when possible. In the rest of the cases, it is manually inserted by the person who connects the thing to a BETaaS gateway. Let's assume that this person is the installer. BETaaS provides to the installer a way to disambiguate the information related to the location and to the type of thing. Disambiguation is implemented in the cases of words with several possible meanings, by means of natural language processing. The installer of the thing selects the correct meaning from a graphical user interface which shows all possible meanings. For example, if the installer defines that a thing is located in a park, first he or she has to disambiguate the meaning of the term park, so the installer will have to choose the correct definition of the term for the thing's context. We have defined a paradigm to represent the functionalities exposed by the different things, and we have called that paradigm thing services. One thing service is created for each of the things that are connected to a gateway. When a thing is connected, its associated thing service is promoted to upper layers. Applications interact with thing services. There is no direct interaction between applications and things. A naming convention has been defined to represent the thing services within a BETaaS gateway. This naming convention is based on some of the parameters associated to each of the things. Specifically, we take into account if the thing is a sensor or an actuator, its location, the type of the thing, the ID of the device, and the ID of its gateway. For example, a presence sensor installed in the main bedroom of Silvia's home will be called getMainBedroomPresence. This slide shows all the thing services that could be created when connecting to BETaaS the different things used by Silvia's applications. the presence sensors of the home alarm system, the temperature sensor of her weather station, and her smart watering valve. BETaaS uses semantic mechanisms and natural language processing to infer information. By means of these mechanisms, BETaaS is able to detect equivalent thing services, which are those associated to things of the same type in the same location, or to classify the location of the things connected to a gateway. For example, Sylvia has installed a presence sensor in her bedroom. BETaaS infers that bedroom is a room inside a home. BETaaS is also able to determine the type of the things connected to a gateway. So, if the watering application downloaded by Sylvia needs a humidity sensor, sensors classified as wetness sensors could be used, as BETaaS knows that both sensors are equivalent. Finally, by means of these methods, BETaaS is able to establish the operator to be applied when different thing services have to be combined. For example, the watering application used by Sylvia would need to combine the presence information of the different presence sensors installed in order to know if there is anybody at home. As a final comment, I would like to say that we are about to publish the first release of the BETaaS platform as open source in GitHub. This first release will include all the components needed to create a BETaaS gateway, so if you download them, you just need to install them on a PC or a laptop and to follow the instructions in order to deploy a BETaaS gateway or even a local cloud of BETaaS gateways if the components are deployed on more than one machine. You will also have 3 or 4 example applications, a generic things simulator to simulate generic sensors and actuators, as well as a cope adapter able to talk both with cope sensors and actuators and with the generic simulator. And finally, all the documentation needed. And that's all. If you have any question, you can send me an email. Thank you for your attention.